Welcome everybody to plan lighting installations. So I'm going to go through this PowerPoint slideshow in the same way that we normally would. However, at the end I might add in a little bit of stuff. This topic is, the slideshow that we're looking at is primarily based on one that we've done previously, which was lighting principles, which you can see on the slides in front of you there. And that topic we did quite some time ago. It talks about different color properties of different types of lights, how we would use those, the efficacy, lighting angles, and the mathematics around that. Now the test that we're going to do for this one is primarily based on that same thing, that same concept. However, there is a little bit in there where you need to create and upload a report and a diagram to illustrate how you would plan the lighting installation for a couple of installations. So that will be given to you in the test, and then you have to complete that separately and send that to me. So at the end of this series of videos, we'll talk a little bit about what the expectations are around that. But for now, we'll go through this. We'll go through this slideshow. So, a few definitions. The term light applies only to visible radiation. So when we talk about light, we're talking about a type of radiation, but it's only radiation that is visible to us. Other radiation doesn't count as light. I guess that should be obvious. Luminous intensity means the luminous flux per unit solid angle in a specified direction. So it's the intensity of light on a specified area. A luminous flux means the light emitted by a source or received by a surface, irrespective of the directions in which it is distributed. It's measured in lumens. So luminous flux is how we would normally measure how much light is being put out by a lamp. If you go and look at a lamp on the supermarket shelf, it will usually have a flux reading on there. It'll say 800 lumens or something like that. And that's also how we would measure. If we have a light meter, we can measure the amount of light that's being received in a given location. And we would use that by luminous flux. Illumination is the lighting of an object or surface. So in here we can see a diagram of what those different definitions mean. So we have the luminous flux in lumens is the total amount of light being put out. Luminous intensity in candela is the amount being put out in a specific location. And the lumens per meter squared, so the illuminance on an area is the amount of lumens that are landing on that area per square meter, and that's measured in lux. Illumination is the lighting of an object on a surface, or an object or surface. Your eyes see two types of illumination on a surface. And natural illumination is daylight from the sun as the source. Daylight illumination levels depend on the position of the sun in the sky and atmospheric conditions. An interesting point about that, not intentional by me, but there is a window just right here, and the sun at this time is coming down and reflecting off the car that's sitting in the driveway, and it's shining in my eyes. You also may notice, I can't actually see the video at the moment, let's have a look. You may notice that this side of my face is significantly more illuminated than the other sides, because that sun is coming in from the window, which is right here. In fact, you can see my hand there, it's gone bright because the sun is coming straight in there. So that's a demonstration of illuminance, or illumination, a natural illumination. Artificial illumination comes from an artificial light source. Obviously, luminaires are used to control this light's distribution. Artificial light may be in addition to natural illumination. So, luminaires in this context, we're talking about our lights, light fittings, whatever they may be. Artificial light in addition to natural light, sure. So sometimes we'll have both. In the situation that I'm in at the moment, I'm going to be using only natural light. I only have natural light. illuminating me for the video. If I were to close the blinds over here, over that light, then I would remove the glare from that that natural light. But obviously I wouldn't get rid of it completely. It's not going to turn the room pitch black. I may then turn on the artificial overhead lighting to give me some additional lighting. And so that would be a case where I'd be using artificial and natural together. Illuminance. Illuminance describes the quality of light. The illuminance received on a surface from a source of light is the luminous flux per unit area of surface. The unit of illuminance E is therefore lumen per square meter or lux. So we saw that on that last slide with the picture. The illuminance received on a surface from a source of light is the luminous flux per unit area of surface. So how much light is falling on a specified area? That's our illuminance. And we just did those ones. Okay, so we have an example here. Calculate the illuminance if total flux of 4,000 lumens falls uniformly on a surface having an area of 10 meters squared. So if we have total flux of 4,000 lumens, that's probably going to come from multiple light sources, or it may come from one. What this question is telling us is that the lumens are going to fall uniformly on a surface area of 10 meters squared. So we don't have to worry about where those light sources are and what angles they're coming down. All we need to worry about is 4,000 lumens falling on an area of 10 meters squared. So our luminance then, it's a very easy calculation. It's going to be our total flux on the surface, which is 4,000, divided by the total surface area. So how much surface area is that flux falling on? And so that would be 4,000 divided by 10 square meters, which equals 400 lumens per square meter, or 400 lux. So lumens per square meter is a lux. Very, very easy example there. Obviously, it's worth noting, I suspect, that in the real world, we're unlikely to come across a scenario that looks exactly like this. If you think about the illumination in any room, look around you right now, and you'll realize that illumination is never uniform. Luminance is never going to be uniform on a specific area, unless you had a single light source onto a single surface. Then you may be able to get in a uniform illuminance. Other than that, you're probably going to be dealing with different angles and stuff like that. Calculation is probably nearly impossible in any real life situation. You may be able to do a theoretical calculation, like if I put this many lights in and this is the angle, how much illuminance will I get? But then in real life, once you install that, there's going to be reflections, there's going to be some natural light, there's going to be encroachment from lighting in other areas. It won't usually mean that there's less light, and usually mean that there's more. So generally when we work out lighting, we're going to work out the minimum amount of light rather than the maximum amount of light that's going to fall. So if we can work out a theoretical minimum, then that will usually cover us. Okay, luminous efficacy. This is the ratio of the luminous flux emitted by a lamp to the power consumed by it. The ratio of lumens of light produced to power input in watts is called luminous efficacy. For example, a 100-watt incandescent tungsten lamp gives out about 1260 lumens. So luminous efficacy is the amount of lumens that are being outputted, 1260, divided by the power input, 100 watts. So it's 12.6 lumens per watt. 12.6 lumens per watt, 1260 divided by 100. Why is this important? Actually, it's really important. It's incredibly important to be able to measure the luminous flux per watt. Why? Because it tells us how efficient that light is, how much light I'm going to get out for. And what is power input? Power input means how much costs me. Remember that I pay for my watts, right? So a 100-watt lamp is going to cost me 10 times more to run than a 10-watt lamp. Will that be more efficient? Well, not if I need 10 times more lamps, then it's the same. So we need to know how much light each lamp will put out compared to the amount of power that I'm putting in, right? As in compared to the amount of to what it will cost me to run it. And this is where I get to bang on about LEDs again. because we know that our LEDs are giving us something like 50 to 100 lumens per watt, so that makes them massively more efficient than a standard incandescent lamp. Our only other considerations then is the quality of the light. Obviously we've talked about before sodium vapor, mercury vapor, that kind of thing. Some of those give out some really ugly, very yellow kind of light, so I might be able to get a very high luminous efficiency or luminous efficacy from those types of lamps, but if the quality of light out of them is so bad that I couldn't use them in a house, then that's probably pretty useless, right? There'd be very limited applications where I'd be able to use those things. Locations where maybe the amount of light and the cost is significant, but the quality of light is not, such as street lighting, which is where we find those types of lights generally. However, in most cases, a LED lamp is going to give us very good quality of light, a very high output, and very good luminous efficacy, which is why they are now taking over from incandescent lamps as the number one most important lighting source in general use. Glare. Glare is excessive contrast of brightness or color. Excessive luminance of an object in relation to its background is a common source of glare. Disability glare can impair vision, with the result that important details are not visible. Discomfort glare commonly occurs where interiors have many bright spots. Often you may not be aware of the discomfort, but its effects are built up and can contribute to your eyes feeling tired at the end of the day. Yeah, so glare, contrast of brightness or color. So a great example of that right now, and again, I'll go back to that natural light that's coming in on this side. And you can probably see that on this side of my face. There's a fair amount of glare there. I haven't closed the blinds because I actually did think about the lighting composition of my video. And I thought for you guys that light coming in is probably quite helpful. It makes it a bit easier to see my face. For me it is a little bit uncomfortable, so maybe on the next part of this video I might close those blinds. And I also thought it's probably important for me to just get some natural light since we're all locked inside at the moment. Just getting some natural light. However, the screen that I'm looking at in front of me and my desk is quite dark compared to that very bright light coming through that window, so that is quite uncomfortable. I would not say it's at the point of disability glare, although if I look directly in that direction, I can see this burning light coming straight off the windscreen of that car. As long as I'm focusing on what's in front of me, I'm not getting disabled by that glare, but it is uncomfortable discomfort. And that's the kind of glare that, as it says here, we might not notice that as we go through our day, but it can make our eyes tired. Maybe even just your eyes adjusting. When you look over here, things are quite dark. Over here, things are bright. And if you're looking backwards and forwards all day, then that discomfort can build up. So let's talk about good illumination then. So if we know a little bit about the types of factors that are going to affect our illumination and affect the people that are using an area that we've illuminated, what does good illumination look like? So good illumination gives us clear vision without eye strain. To do this, the illumination must have strong enough intensity, minimum glare, uniform intensity throughout the illuminated area, and a suitable color. Excuse me. So strong enough intensity means that we've got enough light. Minimum glare means we don't have a lot of contrast, so contrast between brightness and darkness, and not a huge bright spots shining in our eyes. Uniform intensity, so we have minimal shadows and minimal bright spots. We want to ideally have the same lighting all the way through an area, a very evenly distributed light. And a suitable color, as I mentioned before, with some of those cheap high output gas discharge lights, they're going to be very bizarre color rendering. That's like the yellow street lights that really, if you experience that, they do make everything look very strange. And then obviously suitable color might mean we may be able to get enough of the right kind of light output from a light, but if it's red or blue, maybe don't put that in your lounge or illuminate your office. It would just be weird and creepy. The uniform intensity, what does that mean? The intensity of illumination should be as nearly uniform as possible over the whole space to be lighted. Glare can be reduced by diffusing the light through a screen and skillful positioning of luminaires. 4 ways of providing a uniform illumination are to have several lamps suitably spaced, have ceiling, walls and furniture finished in light colours which will reflect light and help to eliminate shadows, use specially designed reflectors, use fluorescent lamps. Intensity of illumination is satisfied by using lamps of adequate strength, 20, 40, 61, etc. Okay, so a uniform illumination then. So several lamps suitably spaced. Well, let's think about that. What's that going to do? If I have, if I needed 4,000 lumens to light a room, and I had one big light in the middle of the room, 4,000 lumens, then I'm probably going to get a big bright spot in the middle of the room and some dark spots out towards the edges and corners. So that's not going to be ideal to make sure I have uniform intensity. So having 4 1,000 lumen lights spread out evenly through the room is probably a better bet than the single light in the middle. That's going to give me better uniformity. Ceiling, walls and furniture finished in light colours. So the reflection, we can use the reflection off the walls and furniture ceiling to our advantage to reflect light around it. Interestingly enough, I guess that's probably the primary reason why the majority of ceilings are white. We don't always have walls are white, but ceilings are always white because the ceiling is our primary reflector of light around the room. If we don't use light colours, if we use dark colours, they will tend to absorb the light. That's not a problem in and of itself, but in terms of our uniformity of intensity, if we have light coloured walls, then the light can continue to bounce around the room and it will reach every spot to an extent. Dark coloured walls will reduce that ability, so the light won't bounce around the room as much, and therefore we won't have as uniform lighting. Using specially designed reflectors. Yeah, probably not that common. You can get specially designed reflectors to focus light in different places. Maybe if your lighting was very, very important, like in a showroom, a gallery, something like that, where you wanted specific light in specific places, you might use specially designed reflectors. And using fluorescent lamps. So fluorescent lamps are pretty good at diffusing light. They tend to spread out their light very evenly in lots of different directions, as opposed to like an incandescent, which is a pretty focused sort of beam. If you think about a fluorescent lamp as that tube, it's not particularly bright in any single location, and it's fairly big. It's got a large surface area, so it illuminates lots of stuff everywhere. Colour. Colour of the light should be suitable for the lighting application. For example, you may want a lamp that produces light similar to daylight. The nearest artificial light source to daylight comes from daylight color fluorescent tubes. Yep, it's very important. As I said before, you don't light your lounge room up red or your office up blue. It just looks stupid. The converse of this is true too. So using that daylight source, daylight fluorescent tubes, that's fine in offices. If you put that in your house, it's going to look strange. We've talked about this before. You'll never see it, or you shouldn't ever see it, because people shouldn't do it. But I think I told you guys a story once about when the little compact fluorescents, the ones that you can put into your normal lighting sockets, first started coming out, and this would be maybe 15 years ago. And I thought that was pretty neat. They were quite expensive back then. They were like $6 or $7, maybe more, maybe closer to $10 to buy one of those. But I thought, yeah, I'm going to swap out all my incandescent lights. I'm an electrician. I understand how this stuff works. I understand luminous, efficacy, and the cost of that $10 bulb versus the amount of power saving and all that kind of thing. So I went and bought a whole bunch of these things and put them everywhere, which I thought was great. And I put daylight ones in because, again, thought I was pretty clever. Let's get the whitest illumination as possible, because it makes things more efficient, yada yada yada. When I put those in the house, it looked like it looked like a horror show. It made the whole thing look like a hospital or something. It just felt weird. It didn't just look strange. It made the whole house feel strange. Particularly the kitchen and the bathrooms, having very, very white lights in those areas. It's just weird and creepy. It was very, very strange because we're just not used to it. So be aware of that. Inside domestic areas, we are used to a light that's a bit more orange or yellow. So that's that. What do we call that? Warm white, and it's a warm color. It feels familiar. If you put daylight lamps, even though daylight is surrounding us all the time, if you put daylight lamps in a domestic situation, it looks strange. Anywhere where you want people to be comfortable, you need to have warm white lighting. You'll notice that in shops and showrooms, they may have white lighting on displays, but generally their normal light is a little bit warmer, and certainly in domestic situations, we want a warmer light. So be aware of that kind of thing. So the color is not just, red or blue or green or that weird yellow light you get from street lights. It can be comes down to what flavor of whiteness you get. Illuminance and colour for good illumination. So illuminance values and lux have been established by international agreement for good illumination in various areas. Illuminance is measured with a light meter or photometer. So this is where the international agreement means that there are some standards out there that says, look, in these types of areas you want about this much illuminance. Generally, as I said earlier, that we would be talking about the minimum amount, but there's got to be maximum values as well, right? We don't want to be working in an environment where you've got enormous spotlights over your head pumping out thousands of lumens directly onto your desk. That will also look like a horror show. So there's got to be a range here, a minimum and maximum, and so obviously people have sat down and worked out what generally constitutes good lighting. What's the minimum, what's the maximum, and then different areas it'll be different, right? So in an area where I'm doing a lot of close-up detailed work, I probably want a bit more light than in a hallway or stairwell, for example, which I'm only in there to move through that space. I'm not doing anything there, so I need a lot less light in that context. Enough light that I don't fall over, basically, is all we really need in a stairwell or a hallway. Okay, so average lumen output, we've seen this before. Pause the video and have a quick study of this. What it is telling us is, for the different types of lights, metal halide, high pressure mercury, sodium, high pressure sodium, how many lumens on average we will get out of each of those types of light for the various wattages. If we did the maths on this, the numbers should stack up about the same theoretically, number of lumens per watt. It looks like they more or less do, but we should be able to figure out from that the efficiency of various types of lights compared to each other. Although not particularly helpfully, the wattage is not the same on all of them. So I guess those are common wattages for each of those types of lights. I'm not going to go through them. Pause the video, have a quick scan of that yourself. Okay. And we have the equivalent here, the amount of light output on fluorescent tubes. This is fairly useful, I guess. It's probably more common that the likes of you and I would be designing a lighting plan for a space that has fluorescent tubes in it, as opposed to the previous slide here, metal halide, high pressure mercury. There's more commercial and industrial applications, so you generally have like an engineer or something who'd be designing a building would probably do that lighting design for that. But in just a generic office or something, your average sparky might be involved with creating the lighting plan for that. Somebody might come to you and say, I'm setting up an office space, I need you to come and do the lighting and power, please. And you might, okay, cool, go and have a look at the space. Hey, here's, do the design, talk to the owner, here's what I want to do. And they go, yeah, okay, cool. So in that case, we would need to be looking at these kind of a table that looks a bit like this. So what does it tell us? So for cool white lamp, a 1500 millimeter, so that's the length of the tube, which will be 80 watts. it's going to give us 5,650 lumens. And read the table, it's going to tell us the same thing. If I got a 900 mil 30 watt tube in white, it's going to give me 2020. Just looking at the number of lumens for the different colors. Interesting that the daylight is a significantly lower lumens at the same wattage than cool white or natural or white. I can't tell you why that is, to be honest. I'm not sure where they've got these codes from and what they mean. Normally I would go with the colors I would expect to see would be daylight, cool white and warm white. Those are kind of the three normal ones, but then it will depend on the brand. The different brands will name them differently. Now, in saying all that, fluorescent lighting is significantly less used than it used to be, and we've talked about that before. In most cases, if you went to buy a brand new fluorescent fitting to be installed somewhere new, you would be looking at getting an equivalent LED. It will look very, very similar. The fitting itself will look very, very similar, but it would not have fluorescent tubes in it. You may also, you notice now I'm going on a bit of a tangent here, but nowadays if you look at false ceilings, you know, the grid ceilings with the tiles in them, you get LED fittings now that are an entire tile. So you take out a tile and the LED fitting fits in there, and it's just a shallow fitting that has a lot of LEDs in it, and that shines directly down. So you would be looking at buying something like that as opposed to a fluorescent fitting. Fluorescents now are mainly going to be repairing existing fittings, like changing the tubes and stuff, in which case these kind of numbers probably don't mean much to you. This is about planning a brand new installation. So when you're planning a new installation these days, unfortunately the numbers for fluorescent lighting are probably not as useful to you. You should be doing that with LEDs. You should have a very good reason to use fluorescents rather than LEDs, to be honest. So if you ever find yourself planning an installation and thinking about fluorescents, stop and say, well, why would I do that? Was there a specific need for me to use fluoros as opposed to LEDs? Okay, so a little bit of maths then. What do we got? Luminous efficacy. Oh, we did this one, right? So luminous efficacy can be compared between the lamp types by taking sample data of each and applying data available from manufacturer. So luminous efficacy equals luminous flux over power input. So taking two different types of lights, we can look at the luminous flux and the luminous flux that lamp would put out, and the wattage of that lamp, and work out what the luminous efficacy is. So if we look at that 100 watt tungsten filament, 1340 watts, 1340 lumens divided by 100 watts gives us a figure of 13.4 lumens per watt. You may notice if you're eagle-eyed that figure has changed from the previous slides where we had 1260, I think, was our tungsten filament lamp luminous output. I don't know why that's different. It doesn't matter. So 13.4 lumens per watt. What does that mean? Let's just reiterate that. So that's the amount of light I'm getting for each unit of energy that I'm putting in. Now, to put that back into really practical terms, the wattage is how much I pay, right? And then the lumens is how much light I'm getting. So the more light I get per watt, that means the better lighting I'm getting for less money. That's what it comes down to. Let's be really clear about this. When we're talking about lumens per watt, we're talking about how much light do I get for the money. If I've got to pay this much money, X amount of watts, how much lighting am I getting for that? If I need to have 10,000 lumens of lighting in a space, then putting all those other factors aside, like color and glare and all that other stuff, then in theory I want the most light for the cheapest input price. Obviously the price of the actual lights themselves will factor in, but if we're working out the ongoing cost, then how much does it cost me to run those lights and how much light do I get from them? So that tungsten filament there gives us about 13.4 0.4 lumens per watt. Now, is that a high number? Is that a low number? Don't know. Let's have a look at a fluorescent lamp. So we've got a cool white fluorescent. 80 watts is our input power, and it's going to put out 5,000 lumens. Well, that means 5,000 lumens divided by 80 watts means I get 62.5 lumens per watt. That's significantly higher. That's about 5 times higher than the tungsten filament. So what that's saying is I will get 5 times the amount of light for my money. For every dollar I spend running my lights, I would get 5 times as much light from the fluorescent as I would from that incandescent. Okay, hopefully that's clear to everyone. Let me know if you need any help on that. The math side of it should be reasonably simple, but this is the formula you would need to remember if you do need to remember anything. If I've got just wondering if I could highlight. Cool. So that would be our formula there. Luminous efficacy equals luminous flux divided by power input. So here we have, we talked about earlier, mentioned that the amount of light required in areas, or general guidelines, is laid out and generally agreed, and here is an example of that. So this tells us the types of areas that we might be looking at putting lighting into. The standard service illuminant, so lux, so that's our, remember lux is our lumens per square meter. So that's how many lumens per square meter that we would need. The position of measurement, so this is where we would want to measure those that lux. So again, remember that our lux is lumens per square meter. So we need to have a location where we would measure that. Like the lumens per square meter, if I measured that at the source of the light, is it's going to be quite different to if I was measuring at the floor or in the corner of the room. So this tells us where we should measure that. And then the color appearance of lamps, so that tells us what color lighting we should be using. Like I said, if you use very white lighting in a bathroom, it will scare the shit out of people because you'll feel like you're walking into a horror movie. You feel like you're about to get murdered. In an office space, maybe not so bad. So these are, again, some guidance on what colors we should be using. So let's have a look at a couple of those. So we're talking about a corridor or passageway. We only need about 100 lux, so 100 lumens per square meter. We should measure that 1.2 meters above the floor, so that's going to be around about waist to chest height on most people. So that's where our measurement's going to be. And we should use intermediate or warm colored lighting. Pretty straightforward. If we're in a stairwell, we want a little bit more lighting than corridors, probably because, as I said before, our primary intention in these types of areas is movement, so it's just enough light to make sure you don't fall over. And stairs probably a little bit more dangerous than corridors, so we need a bit more light. The position of measurement on this one is going to be at the tread, so that's actually at the stairs themselves. So that would mean probably even more light at the source, right? So measuring 100 lumens or 100 lux at 1.2 meters, I'm going to need less light than to get 150 lumens at the floor, because once it gets to the floor, the light is a lot more spread, so more lighting is going to be required, and I use about the same color. If we went down to look at offices, for example, general offices with mainly clerical tasks and occasional typing, that sounds pretty old school, right? It makes it sound like something out of the 60s. It probably is, to be honest. We want about 500 lux, so quite a lot more, 5 times the amount of light on that per surface area of a corridor. And we want to measure that at the desk, so at the location that we're going to be working. That makes sense. And again, intermediate or warm. We could probably, if that little bottom thing goes away, there it goes. If you look down there and see deep plan general offices, business machine and typing offices, and filing rooms, it does probably indicates that this table is pretty old, right? Nobody has filing rooms anymore. They don't have filing tables. It's something that happened before computers. So So a lot of this advice is pretty old, but in general, most of it will still apply. Even if we're doing computer work, this kind of illuminance here is probably still fine. It's probably still fine. Okay, so again, and we have a similar example to what we had before. Calculate the illuminance of a corridor if a total flux of 12 lights where each light is rated at 400 lumens each falls uniformly on a surface which has a size of 12 by 6 meters. So what we're saying then is we have an area of 12 by 6 meters. That's our total surface area, 12 meters by 6 meters. So that's a fairly big room. So our total surface area in square meters would be 12 times 6, which would be 72. It's written down here. So 72 square meters is the size of our space. We've got 12 lights in there, and they're producing 400 lumens each. Now again, it says they're falling uniformly on a surface. That is probably something that we would assume in most cases, as long as we're spreading those 12 lights out uniformly. However, in real life, it's never going to be exactly uniform. We would probably assume uniform lighting across the surface, because any other way is just going to be too hard to work out. But it's worth noting that in real life, there'll still be shadows. You know, unless we were able to have 100 lights, 100 very small lights to give very, very, very diffuse lighting. So our total flux on surface, our luminance will be total flux on surface divided by total surface area. Total flux on surface is going to be the 12 lights that are 400 each, so that's 4,800 lumens divided by the total surface area, 72. So it gives us 66.67 lumens per meter squared, which is too low. If we have a look here, it's too low for nearly everything. We need a lot more lighting than that. Okay, so photometer. That's a really old school photo of a photometer, or you just call it a light meter or a lux meter or something. The photometer is a photoelectric cell connected to a calibrated milliammeter. The scale is calibrated in lux, so lumens per meter squared. The instrument will tell you how much light will fall on the area. So this is a really easy way for us to measure the flux, right? Or lux rather. So you get a light meter, put it on a surface, and it'll tell you how much light is falling on that at that time. That photo and that meter looks like it may be 30 or more years old. Everything about that photo screams old school to me, even down to the lady's fingernails. I don't think you would see that in modern catalogue photography, to have a lady with long painted fingernails demonstrating a technical device like that. It just looks strange. In most cases these days, actually, I'm going to look it up, so if we bear with me for a moment, I'll try and talk and type. So JK is our kind of default for this kind of stuff, right? So if I go on the JK website right now, and here we go, digital light meter, what have we got? So I can get what looks like a fairly basic light meter for $75. $75, and that's going to, it says here, a handy digital light meter for photography, lab work, architectural, engineering and construction applications. Yeah, it looks like it's probably going to do the trick for most applications. There's another one here. We've got something that looks a bit more professional. It's called a professional 400K lux meter with carry case, and that's $209. So it looks a bit nicer. Just do another quick search here for lux meter. Yeah, so it looks like we're talking somewhere between 75 and a couple of $100 to get us a light meter. It's not something I own, and I never have. I've used light meters once or twice, but I guess I haven't really been involved a lot in lighting design, so probably not something I've used a huge amount. But if you're involved in that kind of industry, you may need it more than I have. Okay, so a bit of a summary here. We're about halfway through the slideshow, and after this slide we move more into looking at the types of lighting in different places. So we'll go through this one and then we'll take a pause. Before we take a pause, I think I'm going to do this video in 2 parts, so I'll let you know the first part of the code for this test will be 1-1. The first 2 digits, this will be a 4-digit code. The first 2 digits will be 1-1. So luminous intensity is the luminous flux emitted from a light source in a given direction. The unit of luminous intensity is the candela or candle power. Luminous flux is the quantity of light emitted by a light source, so how much light that thing is putting out. The unit of luminous flux is the lumen. Illumination is the process of lighting an object or surface. Illumination is the amount of luminous flux per unit area that a surface receives from a source of light. The unit of illuminance, E, is the lux, and 1 lux equals 1 lumen per square meter. So that's how much light is falling on a surface over a given area. 4 requirements of good illumination are the light level is adequate, the color output suits the application, the brightness of the source should not be causing glare, the light should be as even as possible throughout the space to be lighted. Luminous efficacy means the ratio of luminous flux emitted by a lamp to the power consumed by it, or another way of putting it is luminous efficacy is the ratio of light that I get from my lamp compared to the cost of running it. Glare is excessive contrast or brightness or color, and a luminaire is a light fitting, e.g. a tungsten lamp or fluorescent light fitting. So luminaire is just a word for a light, any light really. And that'll do us for now, so I will stop that one, have a quick break and come back with the next part.